Yesterday we were just covering some sort of background material in basic computer organization, and then we're going to move on to RAID. But there was a question about something that I put up, was a slide that I don't have here, but a slide showing there's a trade-off between throughput and latency. And I had a diagram where I said if the throughput gets larger and larger, the latency gets larger and larger as well. So it is really a trade-off. You want to get big throughput and small latency is what you would like, but it can be difficult to achieve. And the question that somebody had, I think, and it came back to me through Udaya was, well, why is this exactly? Can you go a little bit, talk a bit more about that? Because I did mention queuing theory was the basis upon which you can understand that. So what I thought that I would do, and I made these slides, just a few slides actually for discussion, to start a discussion in queuing theory. And then we might do more later. And part of the discussion we will end up with is how this queuing theory maybe actually you could apply to your understanding of a distributed storage system and modeling a distributed storage system, and how can this kind of maths help you to do that so that you can work out things like failure rates and so on and things like this, and connect it with bandwidth and other things to see whether the system really can recover and maintain. So queuing theory is a whole area of study, and it's all about, as you can see this diagram, understanding a service, some sort of node providing a service, a job. It's doing jobs. It's executing work. It might be a disk drive, or it might be a computer, or something like that that's doing work. And then the arrival of jobs, and then there's a queue, because when this service node is busy doing something, then these jobs that come need to queue up. And it is applied not just in computing, but obviously it's applicable here. Sometimes these jobs are called customers, in the system, and this is just some sort of service that's being provided. Now, one of the things that you have to change your mindset a little bit when you move from just thinking about a computer that does work at a constant rate to queuing theory is that, for example, let's say the job was just adding two numbers together. You would think that each time I give two numbers, the computer takes exactly the same time to add the numbers together. The numbers are the same size, the same calculations take place, and so it should take exactly the same time to add those two numbers for every two numbers that come along. And if this were the case, maybe there would not be so much applicability in queuing theory, but the time that it takes is a real number. Okay, it's a real number, and so really it's, if you could measure very precisely, you would find that it is not exactly the same time. I don't think you can really have, philosophically speaking, the same time each time you add up two numbers. There will be some very small difference in the time that this machine is taking to add up these numbers. It might be a little bit slower, a little bit faster, and it will do with just two numbers because it's a very simple calculation. It will be to do with just the very much the electronics of the circuit that's adding up the numbers. If the job got much more complicated and there was lots of different calculations and there was lots of conditions that could happen and so on, then the time that it took to take the job, you could understand it would vary. It would vary, that sometimes it would be 5 seconds and sometimes it would be 5.1 seconds and maybe it's 4 seconds. And so, in fact, even for simple work, we don't assume that it takes always the constant time to do the job, but we assume in queuing theory that this is a random number. How long does it take to do the job is a random number, and indeed the arrival rate here of jobs as well, we're going to call, that is random, or random process, if you like, as well. So the fact that this service actually has some variance, that it's a random, it's a random number, it has a variance as well, it has a distribution, means that there's some very non-intuitive things that start happening with the system. Which we're going to understand here. Now, in queuing theory, there's there's a nomenclature around naming the kinds of systems queuing systems that you want to analyze. This is called an MM1 queue because these processes are Poisson process for the arrival of jobs. We just assume that jobs fit a Poisson distribution as they arrive, so they're kind of randomly arriving, and that the time that it takes to service each job is described by an exponential random variable as well, distribution, and so the M and the M kind of refer to that, and then the 1 just means that there's one service node. We can make other assumptions about the distributions of these things that will lead to different kinds of outcomes. So we could have just general distributions and so on. It becomes a bit more a different kind of calculation. And there's a lot of different kinds of things. So you can have multiple service nodes. You could have K service nodes and a lambda that's going into different numbers of queues. This is assuming a kind of infinite queue. So, it could get infinitely large. You could have as many, so there's no buffer constraint. But in practice, there will always be a buffer constraint. You don't have a computer with an infinite amount of memory. There's a finite amount of memory. So this queue in practice is always finite, but for some analysis, we just assume that it's infinite and see how big does it get. And that is actually, in queuing theory, what we're trying to understand really is the properties of the system. In principle, in this very simple system, how big does the queue get? If I look at the queue in a stationary state, I just come and look at the queue at some point in time, I see a certain size. If I go away, I come back, I look at it again, I see a different size. I come back, I sample the size of the queue, then it will give me some sort of distribution, some sort of average number of customers or jobs waiting in the system. And it might be 0. And when we look at that size, actually you'll see, we're including if there's one being serviced right now, plus the queue size, if it happens to be there. So it might be 0, there's nothing there, the system's not doing anything, or there might be one job that's being executed and one job in the queue and so on. So that'll be an integer number. So that's the aim. We want to understand, in this case it'll be the queue, or equivalently, the bigger the queue, on average it gets, then the expected waiting time in the queue. So if I come as a customer and I stand waiting for service, how long do I wait before I start getting service? Right, and then that little bit more before I'm completed, my service is completed. We can understand these kinds of things with queuing theory. So that's kind of what we want to do, and these things can get very complicated. As I said, you can have more. So you can look at multiple computer system, and have multiple service nodes, and service nodes can sometimes fail. So you can have then when the service node fails, it goes into another queue, which is the repairman service, which repairs the failed node, and the repairman may be busy. The repairman is providing a service to fix the failed service nodes. So how long, if a node fails, how long is it before it returns to service? How long does it take to repair the node? So there are models that include that in queuing theory as well. And maybe you have multiple repairmen, repair services. So again, this becomes very complicated, but all of queuing theory allows you to understand this and then sort of see ultimately what is the throughput of the system, the latencies in the system, how big will the queues get? If the queues get too big, you can run out of memory. If you have finite buffer space, all these things have to be stored in memory. Then you start having a problem. You have to drop stuff, so you get loss in the system, or you have to, like back pressure, you sort of have to say, no, I can't accept any more jobs. You wait somewhere else. Okay, you just have to wait elsewhere. You can't wait in the queue, right? So it's kind of like blocking. We talk about a system that blocks at that point. So that's what we want to understand. And what I have is just a few slides. There's not many slides here. I'm not going to go through lots of proofs and so on. But I do want to try to give a little understanding to see if the intuitive understanding of why the throughput goes up, the latency goes up, what is the trade-off. So just before we do that, so we talked about that these jobs come, so the service time is an exponential distribution. I think you can see there with mu as the rate, right? And so it has a probability of of the service being tau, for example, as given by this exponential function, you know, or 0 if tau is less than 0. You know, so jobs never take negative time to do. They're always, you know, something 0 or more. So that has that, and you can sort of see I've got an arrow here in time, and these little ticks are, for example, the time when a job was completed. You know, and so the time interval tau here is the time that it took to complete this job. You know, so the service node completed a job here, and then it takes some time to complete another job, and then it takes some time to complete the next job, and so on, right? So this is how you can represent things being done in time. So the exponential service time is giving you these time intervals here, these contiguous intervals. Now, this is just one realization of a random process, right? So this, you know, this could happen all day. It's random process. There could be different realizations of this. Now on the same diagram, and I don't want you to get confused, and I'm just using the same diagram to show that that the arrival rate of jobs, the Poisson distribution that we said earlier, is actually very related to the exponential distribution. There's a very close relationship between Poisson distribution and the exponential distribution. The Poisson distribution is saying, you know, if I take a time interval t, then the number of jobs that arrive in the interval, you know, is some integer. Maybe no jobs arrive in the interval. Maybe one job arrives in the interval. Maybe two jobs, and so on, right? So there's a probability for the number. There's always an integer number of jobs. You don't get half a job arriving in the interval. And that can be written here. So the probability of x jobs arriving in the interval t is given by this equation, which sort of fits the Poisson distribution, which has an exponential part to it. And again, so here's the lambda now as the arrival rate of the jobs. Times lambda t to the x, all of this divided by x factorial. And the relationship between them is, if you know, I could write on the board, but we can just sort of look at the equation and think. If we put x equal to 0, so if I say what is the probability that no jobs arrive in this interval t, then you know the x equal to 0 makes this 1. 0 factorial is 1, right? So these kind of things disappear, and you're just left with e to the minus lambda t. Probability that, you know, no jobs arrive in a time interval t with a rate lambda is e to the minus lambda t. If I wanted to ask, well, maybe I should write. If I wanted to ask then what was the probability that at least one job arrives, it will be 1 minus e to the minus lambda t. You know, at least, so this was the probability that, you know, that nothing arrived, and so that at least that not nothing arrived, the probability that not nothing arrived, then it's 1 minus e to the minus lambda t. Now, that's actually a cumulative function. If I then go and derive it and get the probability distribution function, then I get lambda e to the minus lambda t, which is you know in the same form as this. It's just mu is lambda in this case, right? So these two, you know, they're very much related. It's just that we like to talk about arrival of jobs as a Poisson process, and we like to talk about, you know, the service time as being an exponential random variable. So we're interested in the queue size. So the queue size could, you know, or actually not just the queue size, but the customers currently being serviced, if any. So the 0 means there's nobody being serviced and there's no one in the queue. There's one person being serviced and there's nobody in the queue. There's one person being serviced and there's one person in the queue. So actually these are all the possibilities. And it's infinite, right? We have an infinite queue size for analysis. We just say, well, it can go forever, right? And you know, as people arrive, as jobs arrive, then we kind of get bumped up through this state space, and as things get done, then we go backwards the other way, right? So this is a kind of Markov analysis, and you can write a transition matrix, Markovian transition matrix for this. You know, I think it's kind of, you can see, you know, where we're going if you've studied that. And now, so the state of the system is described by this. Clearly, we need lambda, the arrival rate, less than or equal to mu. If lambda were greater than mu, then, you know, we're taking more steps this way on average than we take steps that way, right? So you kind of take 2 steps this way, 1 step back maybe, and then another 3 steps this way, and then, you know, 2 steps back maybe, but then 4, you know, so you end up going to walk through the wall, you'll end up going off to infinity. This will just go and keep going and going and going if lambda is not less than mu. So it needs to be less than mu to have a stable system. But then, so some of the, I'm going kind of quickly because I'm not going to go through all of the maths to derive it. We could look at it later if we wanted to, but, you know, so what we write down is, what we can find is that the utilization of this system is lambda on mu. Lambda is the arrival rate, mu is the, you know, the service rate. What I didn't say actually, lambda and mu being the arrival rate and the service rate, 1 on lambda is the mean time, right, to do the to do the job, and 1 on mu is 1 on lambda is the mean time for arrival, and 1 on mu is the mean time for, that's the means of these functions. So we can write the utilization as lambda on mu. So as lambda gets bigger and bigger and bigger, then we're sort of, the system is being utilized more often. It's the average portion of time actually that the service node is busy. So if lambda were half of mu, then the service node is busy half of the time on average. If you come and look at the service node, you know, half the time you look, it will have a job. It will be doing something. Half the time it will be idle, not doing anything. If lambda is always less than mu, so this you know, for a stable system, this utilization has to be less than 1. And now, you know, when you have a Markov chain like this, you can sort of ask for what is the stationary distribution. So if you just, it doesn't really matter which queue size you start with. If you start with nothing in the system, or you start somewhere out here, after a sufficient period of time, you could ask yourself, what is the probability of being in these states? There's a stationary distribution. So after a sufficient period of time, the system will exhibit a property, and that probability is given by this pi I, which is the 1 minus rho times rho to the I, is the probability that the state equals I that we're in. And again, you can figure this out, you can derive, if you apply some Markov theory to do this. I thought that was going to be a fire alarm. It's a phone. Anyway, so the average number of customers in the system then, again, this is something that comes from the analysis, is rho on 1 minus rho. That's the average number of customers in the system, including the one that may, you know, be being processed. So look at this equation then, you know, rho should be less than 1, but what happens as rho gets close to 1? Right, this thing, what happens to this as you take the limit as rho gets close to 1 is that this function, it goes off to infinity. Right? So that's a sort of asymptote off at infinity at that point. So this is actually the equation, this is the result that gives us the notion that there's a trade-off between throughput and latency. If rho is very little, then the you know, very small, you know, 0.1 or something like this, then the service node is not doing much. It's not being utilized very much. The throughput is low. But the number of customers in the system is also very low on average. Right, so if a new customer comes along, they don't have to wait very long. There's only one maybe customer there, and then they go and they get service. So the latency is low. But as rho gets bigger, if you want to try to get higher throughput, and you try to push the utilization, and you get closer and closer to, you know, making that service node work 100% of the time, so the throughput is getting maximum, then this shoots off to infinity, which is the number of customers in the system. So you could be waiting for near an infinite amount of time before you get service. The queue becomes nearly, you know, it approaches an infinite size. And so this is why the trade-off exists. And it only really exists because we assume that the service rate is a random variable. If it was just if it was a deterministic thing, it took exactly the same time, then, you know, you wouldn't get a gradual. Did I just turn off the laser pointer? Maybe, I don't know. Yeah, you wouldn't get a gradual increase, it'd just be like a step function. Once you got to the maximum rate of the system, then suddenly you'd see that the queue would start building up because you've just you've got past what it can do. But the queue will start getting quite big even before reaching the maximum rate of we talk about the average rate of the system, right? It will start getting very big, and indeed it will get that big. How big it gets could exhaust the size of your memory. So if you don't have an infinite size queue in the computer, so you have a finite size queue, and it can exceed that, right? So even though you've not got full utilization of the system, you're still exceeding the amount of buffer space that you have. So that's kind of, I hope, gives just a little insight into why we had this trade-off between the throughput and the latency. And what I want to say more is that I actually did work with queuing theory a few years ago, a while ago actually, with distributed systems, and I was looking more at communication properties. But I think you can apply as well some of the same maths and principles to maybe analyze your distributed storage, because one of the things you can do, and what I did was I had two sets of nodes, of computers, right? These are the nodes in the system, and one of the sets was the working set. And one of the sets was the failed set. Yeah. So a node, if there's a computer in this set, then it's not operating. It's not doing anything. It can't be contacted. You can't communicate with it. Maybe it's lost its data as well. So it's completely. But if it's in this set, then it's working, and the nodes in this set can communicate with each other. That they have the data. They're working properly. So what you can do is you can sort of say, well. Nodes go from the working set with some sort of rate mu, and they go from the failed set back into the working state with some sort of rate lambda. So you have this kind of what in peer-to-peer we call churn, where nodes, eventually everything fails eventually. I don't think this is again philosophical, right? You can't build something that will work forever without failing. Right? It will fail. Maybe the second law of thermodynamics or something tells us this. It will fail. Eventually things will fail. They need to be repaired. So they move from a state where they're working, they die, and they go, and then in this model at least, then we put them into the failed set, and it might take some time before they get restarted. It might only take 5 minutes or an hour or something like this. They need to be rebooted, or maybe it's the failure is much greater and you need to replace a motherboard or some memory, there's some power problem or whatever. So there's they get repaired, right, and they come back into the system. Now if you think of these nodes as maybe n nodes in total, so if you add these up, you get n in total, then you sort of have a fraction of all of your nodes in your distributed system that are working, and a fraction are over here. If lambda and mu were equal, you'd have about half the nodes over here and about half the nodes over there at any one point in time. Once you get into the stationary state, right, that's sort of what you will see. The magnitude of the lambda and the mu is what gives you. Is lambda and mu in hours, or is it in minutes or days? Or so how often do things fail and go backwards? And we're not talking they're failing every second or something like that. So the magnitude gives you the scale of the system, of your analysis, and then the proportions between the lambda and the mu sort of say, well, what do we see? Are most of the nodes working or not? Now, if you think of these nodes as storing data, and later you'll be thinking, you're having erasure codes and so on across that, then you have to sort of understand, nodes are constantly failing. Right, and coming back as well. Now, as they fail, you need to repair or recover data. You need bandwidth to do that. There's only a certain amount of bandwidth. Again, this is kind of a physical constraint that we have. There's only a certain amount of bandwidth. So, presumably you could use this analysis to understand, do you have enough bandwidth to support your your codes that you come up with, because the codes require a certain amount of transferring of blocks from one place to another and so on and so forth. Depending on the lambda and the mu and exactly what those parameters are, you know, maybe it does or doesn't support. One more thing that I will say is that thanks, one more thing that I will say is that you know, this analysis ultimately will give you, at some point, it gives you a probability that everything fails. Right, so the whole system could fail. And that probability is there, but it's very small. Right, so you can always work this out, and your codes will never really recover from. If everything fails, what can you do, right? If everything burns down, then there's nothing really more that you can do. But you can sort of ask then, what is the probability, you know, of if I have a code of a certain size that can recover from a certain amount of failure, what's the mean time to failure? Sometimes we talk about, so it's not in a failed state. Now, what is the average time until this system will fail? Will it be 10 days or a year or whatever? On average, you can start to work these things out. So I think you can get a lot out of queuing theory if you want to. I mean, you know, you're all here to study coding and finite fields, and you're all, you know, in that mindset. But, you know, there's some very interesting stuff here for you to think about. And as I said, maybe we think a bit more about it. I'll just go to the last slide. One thing I wanted to say, I did work in this area a bit in applying queuing theory to some stuff. If you want to, these are the books that I would recommend to use. They're actually from the same author. That's just the second edition. The first edition I gave to a brilliant student of mine, Rajiv Ranjan. He was with Raj Kumar Boyer Bureau as well. But he took it on an aeroplane and spilt coffee on it. And so he didn't give me that book back. He said, no, I don't, you know. So I went and bought the second edition of this book. It's very good. It's probability statistics queuing theory with computer science applications. It's specifically for computer science discussion. So if you're interested, I would recommend this book. I actually like the first one more than the second one because the second one has a different layout of some of the material in it that I got used to the layout in the back. This one had an appendix for all of the models. It was quite nice, and this one sort of puts it throughout the chapters. There's a bit more material in the second edition though, and I think it's corrected some of the errors that were in the first edition. So, you know, this is the kind of my Bible that I go by when I look at queuing theory, and you know, you might find that you can get a copy somewhere or something like that. So all of what this slide set was about was a single computer system, the organization of a single computer. Now RAID 0, you know, there's a lot of different RAID types and ways of configuring disks and encoding across the disks to try to give some redundancy, but also changing the performance of the disk drives. Essentially, if you put multiple disk drives together, then you get more throughput or more IOPS or something like that. So there's RAID 0. It's not really a RAID because it doesn't have any redundancy, but it's often included as, you know, part of the different types of RAID. It just distributes the blocks over the available disks. So you can, instead of having just a bunch of disks where you try to manually load them in you know, so that they're equally loaded and you're getting the proper usage of, you know, maximum usage out of all of them, you just start distributing things across all of that. And then, you know, all of your disk drives can be busy at the same time when you're writing a large file or something like that. And indeed, even if it's small things that you're reading, the IOPS can go up because you can be using multiple disks for doing that. And then RAID 1 is mirroring. So now we actually have some redundancy, you know, where you've got a couple of disks or something like that, and you've got a copy. If one of the disks were to fail, then you can reconstruct it simply by copying from the other disk, bring the copy across. But, you know, RAID 1 has a problem. While it has this redundancy, writes have to go to both of the disks at the same time, right? So you're really not writing any faster than you're writing to one disk because you've got to keep both of the copies maintained if you make changes to the blocks. So there's these diagrams. I sort of just had a look on Wiki. These are the standard diagrams that we all see when we talk about RAID. You know, RAID 0, you can see the blocks have just been distributed across. There's no redundancy. We don't see the same block more than once. Each block is just once, A1, A2, A3, A4, and so on. and then RAID 1 where you've got, we've really just got a mirrored disk. It's just mirroring. So, you can get twice the read performance from this thing. You can be reading different blocks from both disks at the same time, so you've got better performance that way. But what as I said, as you write, if you update and you're writing, if you update A2 here, you've got to update it over there as well. So there you're back to just the performance of a single disk. If one of the disks fails, then you can reconstruct it just by, you have to go through a copy process of just copying all of the other one across. So that's RAID 0 and 1. It's kind of common in maybe in small systems. I have a RAID 0 system, I think I said, at home. With 3 solid-state drives, that it's quite good. I put a lot of media on that and get a lot of performance from it. I don't like using that on my, because I always feel like I'm wasting a disk drive somehow. I don't need the redundancy on my own machine, right? It's not that important. If I lose all the movies that I have stored on the computer, it doesn't matter to me so much, right? So now RAID 2 and 3. So RAID 2 and 3 are kind of not really much used. In practice, they're somewhat expensive. They have different kinds of protection, and your data's talked about parity, error correcting, and so on. I mean, the diagram probably is better to look at rather than looking at the text. So here we've got, a bunch of disks that are actually the stripes are at the bit level rather than the block level. So you're trying to really have a lot of disk drives work all at the same time. So you're reading a lot of data, actually. You're getting a huge amount of throughput by having all the disks. So when you start reading the blocks, you've got all these disks working all at the same time. The problem is that it's at the bit level or the byte level for RAID 3, there's 6-byte blocks. The disk drives have to be synchronized. You can't have some disk drives working a little bit faster than the others, and then otherwise, so what if that were the case, then things that you read would get out of whack. You'd be reading some bits for some blocks and whatever, some parts of the file somewhere, and it wouldn't work. So these disk drives need to be synchronized with each other. They all need to work together. To do that, it's very expensive. You need special components in the disk drives to make it work, and so this is very good for high performance reading. Like if you have, say, maybe a video on demand system where you need to read a lot of data, you never change the video. Writing, of course, you sort of write to all of the disks, but for high throughput. And I think even if you made solid state drives, you'd to make it work on solid state, you'd have to have some kind of electronics in the drive controller again to synchronize, to make sure that it's all happening asynchronous. So because these things, even though they're all built the same, they have you get a drift ultimately between the components. They all work at slightly different speeds. So you'd need extra electronics to make it work on solid state as well. So RAID 4 is the data is interleaved, striped on all the disks in relatively small units, maybe blocks or tracks or cylinders. And there's a dedicated disk holding parity. Reads read from one data disk. Writes, though, have to read the data block and the parity block, compute the new parity, and then write the data block and the parity block back. So, so for reading, the RAID 4 has all the advantages of the striping. It evens out the load and increases the transfer rate. You can be reading from different disks, but for the writing, it can become kind of slow because you've got to first read, the parity block, the data block and the parity block, and compute the new one. So you've got the parity over here. So if I write, to A3, I've got to be able to compute the new block and write back down here, which means that it takes, it's slower than writing to a single disk. The write speed's got slower now in order to maintain the parity when I make updates to the drives. But when I'm reading, I can get the performance of, maybe up to like 3 of the disk drives that I can get when I'm reading. So RAID 4 has this problem that it's got all the parity stored on one disk. Again, it's not really used very much because there's better systems to do. So the RAID 5, it tries to distribute the parity around on the disks somehow to ensure that there's no disk that becomes a bottleneck for the writing. So the parity blocks kind of get spread out like this, and then so when you're doing a write, well, it might be this disk that that you use, or that disk that has and so on, right? So they kind of get spread out, and so it sort of evens it out a little bit, but still the write is still kind of slow because you've got to write to 2 disks rather than 1. The other thing I might mention is that this is a very simple kind of, this is the parity for those blocks. Some of the RAID codes will sort of, the parity is not just across the stripe there, but it might be those 4 there or something that, those 3 that create the parity. And so they sort of break up the things in different ways. We won't really go into that. I don't know if Hideo will talk maybe later or something like that. And so there's RAID 5, and this is okay, but the problem now is that if one disk fails, you can kind of reconstruct, if this disk were to fail, you could reconstruct a parity, you could reconstruct B3 and so on, you could reconstruct the disk by from the other disks, but if you get another failure while you're reconstructing, then things can go wrong. So this is just saying the performance, but I sort of said that the RAID 5 will do almost that many read ops and between this many write ops. But if there's a crash then in the middle of a kind of problem with RAID 4 and 5, then you can lose data. So there are different ways to solve it, but RAID 6 then, I'm kind of going a little bit quickly through the slides. RAID 6 will have a bit more redundancy now, so you can kind of tolerate more than one failure of the system. When you're reconstructing, it takes time to reconstruct. You pull out a disk, you put in another one. It does take a while. I've had it happen with a few servers that I've been maintaining, and it can take a while to do, and you don't want another thing to fail, but in this case you can kind of tolerate a bit more failure. So there's RAID 6. And then there's a whole heap of things that people come up with, different configurations that use these basic configurations to try to improve performance, improve the redundancy somehow. So it's kind of what we call nested RAID, right? So I've just given a couple of examples I found. There's many more that you could think of perhaps yourself that do various things. So here you've got RAID 0, which is no redundancy in this group here, and there's no redundancy in this group here either, but these 2 groups are mirrored. Well, I should say this group is mirrored here, right? So this is a mirror of that, right? You can see the same numbers. So, if something were to fail here, if this disk were to fail, we can reconstruct it from over here, right? Or if this disk were to fail, we can reconstruct it over there. Or indeed, if this whole 2 disks were to fail, I can see that I can reconstruct it, right? But what I can't handle is if this disk fails and that disk fails, then I lose my data, right? So different kinds of failures. One of the things I didn't mention even before when I was talking about queuing theory and failures there is that all of what we discussed was assuming independent failures. That all of these nodes are all independent of each other. There's no correlated failure, right? And correlated failure is quite a bit different. So you might think if this group is sitting in the same area of the computer, or somehow that, and maybe if the failure might happen because of the power supply that's connected to these 2, because they're somehow that they're running off the same subsystem, so you get correlated failure where they both go down together. And maybe in a distributed system you see correlated failure because some of the nodes are in one building and some of the nodes are in another building, and that whole building just goes down for some reason. All of those nodes go down together, so they're not independent. Now, correlated failure is a bit kind of different analysis. You can't make the same sort of assumptions. It's very nice mathematically to actually assume independence, right? The mathematics becomes simpler if you do that. And I think you could see that that correlated failure might come into the analysis here, depending on exactly how the system is built and what are the other components that things rely on. You know, fans, you need fans to cool things down, and that could lead to some correlation between the failures and so on. This is a much bigger system. It's kind of a, you know, a RAID 5 here, and then what is there? There's some sort of duplication over there, so I can sort of tolerate the, well, not duplication, sorry, this is it's just a striping, right? So I can tolerate the failure of one of the disks in here, and one of the disks in here, and one of the disks in here, and so I could tolerate three disks failing, actually, so long as they all fail in different areas, right? And then they could be reconstructed each independently. But if two of the disks in one of these RAID 5s would have failed, then I can't reconstruct them. So you can sort of see how this is helping. The striping gives us you know, more throughput. You know, we've got more disks ultimately working for us, so we get more throughput and more IOPS and that sort of thing. And we've sort of changed the properties of the you know, the likelihood of it failing, right, of the system failing. And, you know, again, you might think and apply queuing theory to disk drives and say, you know, you can sort of see that they're either working or they're being repaired, you know, and sort of swap them between, you know, two states and sort of say, well, you know, how long on average will it be until this system fails? Because it will fail eventually. That's my philosophy. Everything will fail eventually. There's just some probability of it happening, and you can kind of work that out. And so you could do that. So there's, you know, just some background again on RAID, and as you go through the course, you'll see, you know, how this kinds of concepts get extended to distributed storage systems and so on. But this is where it sort of all started, I guess, in the basic computer system. So then, just a couple of slides left is just, you know, so beyond that, and as we talk about backup, and so remember our memory hierarchy, we go all the way down, and then you start backing things up. Sometimes you might even call it cold data, but I think even backup maybe goes beyond cold data, where you really want really big. This is a little bit old. These 100 gigabyte ultra tape, you know, these cartridges. Probably the sizes are much bigger now for tape. It's very cheap. I don't even know if people use tape really anymore. Probably not. So some of these numbers are a bit slow, a bit old. But really, then you get to robotics. We're actually trying to start at Melbourne University a collaboration with NetApp, which is a really big company that provides data storage and so on. They want to somehow get their products and services into the university. So there's some interesting things there. But, you know, I've never actually walked into a room that's got all of this, but it'd be very, you know, this is kind of, I guess, where the storage ends up, right? This is some huge storage thing, which is all robotic arms that move around and find cartridges and tapes, and, you know, the latency becomes very high to get the data and so on. But, you know, it stores a massive amount of data and this kind of thing. And it would be really interesting, I think, to work in this kind of area. It's just that I'm not doing. And there's this last slide on I/O processors. Ultimately, if you've got a lot of I/O, you end up with computers that are just dedicated for just transferring data around the place. That's all they do. They just transfer data, whole processors. A graphics card is actually an example of an I/O processor that's transferring data, you know, from the computer to the screen. It's just dedicated for I/O, and the same thing with storage and so on. So it's kind of the end of the background material. If there's any questions.